Hi everyone, today we're going to be talking about present values of annuities. Annuities can also be used to describe scenarios in which a person receives equal periodic payments or withdrawals. These are often thought of in the context of retirement accounts. The single sum of money required to purchase an annuity that will provide these payments at regular intervals is called the present value of the annuity. So, example 1 says, suppose you want to receive $100 at the end of each year for 5 years, an account that paid interest at 10% compounded annually. How much money would you have to invest upfront as a lump sum for this to happen? Okay, so I've written my little timeline here, and at the end of the first year, we would want to get $100, and at the end of the second year, end of the third year, at the end of all the following years, we would want to receive $100. Now, the way that we want to think about this is that this is not worth $100 right now because that is a future value. And so the amount of money that $100 is worth right now is actually equal to 100 divided by 1 plus our annual interest rate, which is 10%. So in previous examples, we were given $100, and after a year, it would have been 100 times 1 plus 0.10. But because we are now given the future value of $100, we're trying to calculate its worth right now. So instead of multiplying, we would be dividing. Now, this $100 in the future is really currently worth, I'm going to write this as 1.10 squared, and that pattern would continue for all of these. So this would be $100 divided by 1.10 cubed, and this one would be $100 divided by 1.10 to the fourth power, and this one would be $100 divided by 1.10 to the fifth power. So these numbers here represent the present value of all of those $100. And so the amount that we would need to pay now is going to be equal to the sum of the highlighted values. So ultimately, I want to take these and add them all up. So the way that we do that is just like any other time where we would add up a geometric sequence. And so we would follow the formula. S sub n is equal to the first term times 1 minus the common ratio to the nth power over 1 minus the common ratio. Now here we have 5 terms, so our n value is going to be 5. And our first term is 100 times 1.10. And then we have 1 minus, what is our common ratio? Well, we are multiplying by 1 over 1.10 to the nth power, which in this case there are 5 terms, so our exponent would be 5, over 1 minus 1.10. Sorry, that should be a fraction, 1 over 1.10, like that. So I went ahead and I plugged that into my calculator and I got $379.08. So that is how much money I would need to put up front in order to get basically $500 at the end of 5 years, where it's giving me $100 at the end of each year. So if we are talking about the present value of an ordinary annuity, we say that if a payment of R dollars is to be made at the end of each period for N periods from an account that earns interest at a rate of I per period, then the present value of this ordinary annuity would be given by that formula. Maybe take some time to see how you could kind of generalize that from the previous example. Example 2 says, find the lump sum that one must invest in an annuity to receive $1,000 at the end of each month for the next 16 years if the annuity pays 9% compounded monthly. So essentially we are trying to find the present value of this ordinary annuity, and that is denoted capital A sub n. Sometimes you'll see it written as PV for present value, but our textbook uses A sub n, so I'll try to stay consistent there. So that is the thing that we don't know and are solving for. We know that the regular payments are equal to $1,000. And we know that our interest rate is 9%, but that is compounded monthly, so we need to divide by 12 to get 0.0075, and the number of time periods is 16 years, but we are compounding monthly, and so 16 times 12 is 192. So let's remind ourselves A sub n is equal to the regular payments times 1 minus 1 plus the interest rate to the power of negative n over I, like that. So A sub n is equal to 1,000 times 1 minus 1 plus 0.0075 to the power of negative 192 divided by 0.0075. And if you throw that into a calculator, you should get approximately $101,000. Sorry, excuse me, $101,573. So that is how much you would have to pay so that for 16 years, you get $1,000 at the end of each month. Example 3 says, suppose a couple plans to set up an ordinary annuity with a $100,000 inheritance that they received. What is the size of the quarterly payments they will receive for the next 6 years while their children are in college if the account pays 7% compounded quarterly? So in this case, we know that the present value is $100,000, but we don't know the size of the regular payments. And we know that the interest rate is 7% compounded quarterly. So we would do 0.07 divided by 4. Which is 0.0175. And then the number of terms or the number of periods, it's for 6 years, and we are compounding quarterly, which means 4 times per year. So that's going to give us an n value of 24. Okay, so we're just going to plug those values into our formula. We don't know what r is there, so Then we have 1 minus the quantity 1 plus 0.0175 to the negative n power, which would be negative 24, divided by 0.0175. And so R is going to equal 100,000 divided by that big ugly thing. Okay, and if you throw that into a calculator, you should get that that is approximately $5,138.57. So that is the amount that they would get in quarterly payments at the end of each quarter for 6 years. Example 4 says an inheritance of $250,000 is invested at 9% compounded monthly. If $2,500 is withdrawn at the end of each month, how long will it be until the account balance is $0? So here we know the present value is $250,000. We know that the regular payments are in the amount of $2,500. We know that the interest rate is 9%, and we know that it is compounded monthly. So 0.09 divided by 12 is 0.0075. And the thing that we're solving for is n, which is the number of months in this example. So we want to go ahead and try to solve for n. So let's plug these values into our formula. Okay, so the first thing that I'm going to do is I am going to divide both sides of this equation by 2,500. And if I divide both sides by 2,500, we get 100 is equal to 1 minus 1.0075 to the negative n power over 0.0075. And now I'm going to multiply both sides by 0.0075. And if we do that, then we get 0.75 is equal to 1 minus this value. And then I will subtract 1 from both sides. So if we do that, then we get negative 0.25 is equal to negative 1.0075 to the negative nth power. And I could divide both sides by negative 1. And if I do that, I would get 1.0075 to the negative nth power is equal to 0.25. And now I'm going to take the natural log of both sides. I'm going to skip a step, so I get negative n times the natural log of 1.0075 is equal to the natural log of 0.25. And then if I solved that for n, I would get n is equal to negative natural log of 0.25 divided by the natural log of 1.0075. So I threw that into my calculator, and that is approximately 185.5. So really, because this is measured in months and it happens at the end, we would say that the account balance will be $0 after 186 months. Maybe I'll write that over here. So account balance will be $0 after 186 months.